Assalamualaikum warahmatullahi wabarakatuh. A very good day. So in this slide, we will discuss about fuel spray behavior test, where this test is actually under the second category of fuel test, which is the fuel spray test category. So previously, we already discussed the first category of fuel test, which is the fuel droplet test that consists of fuel evaporation test and also fuel deposition test. However, for the second one, we will discuss about the fuel spray investigation. So now we discuss about the fuel spray behavior test investigation that conducted by Hawi et al. 2019. So this schematic diagram shows the schematic diagram, simplified schematic diagram or apparatus that used by Hawi et al. That consists of mainly a spray chamber, um, injection system that used to produce fuel spray, camera system that used to capture the spray pattern, and piston system that used to increase the pressure in the spray chamber. So actually, Hawi et al. Investigate three type of fuel. However, in this discussion, I only discuss in terms of the result for 100% for typical diesel fuel B100, or we call DF, and also pure biodiesel B100. And in terms of injection pressure, Howie et al. Investigate three type of pressure: 50 megapascal, 100 megapascal, and also 150 megapascal. However, I will take the result for 50 megapascal, just for comparison in terms of different result that obtained for diesel and also biodiesel. So this is I call the one of the result in terms of spray behavior that captured by Hawi et al. 2019 in terms of spray pattern for diesel and also biodiesel. So in this photo shows the what I call the spray pattern, and this photo captured by using high-speed camera. So from the photo in this investigation, as shown in the figure in the slide, so Hawi et al. Measure the liquid penetration, represented by L, vapor penetration, represented by S, and also cone angle value, theta. Okay, so now after this, we will look at the value of L, theta, and also S for B100 or DF, and also D100 or DF that represent for typical diesel fuel, and also B100, which is represent the pure biodiesel, 100% biodiesel fuel at injection pressure of 50 megapascal. Okay, before we discuss about the result that obtained by Hawi et al. 2019 in terms of vapor penetration, liquid penetration, and also cone angle value for diesel fuel and also biodiesel fuel. Let first we look at the parameter for spray characteristics. So in this figure shows the injector tips, spray axis, and also spray contour of fuel. So the distance start from the from the injector tip to the end of fuel spray is represented by S symbol, and S actually equal to spray tip or vapor penetration, and L is the liquid penetration, and theta refer to spray cone penetration, where normally in order to measure theta, so we need to consider the distance of from the injector tip to half of spray tip penetration, S/2. That's how we can calculate the value of theta. So in terms of liquid penetration result that obtained by Hawi et al. So we can see that the graph shows the liquid penetration in millimeter versus time after energizing the fuse spray during the investigation. So green color line represent the data for the result for D100 diesel fuel, and blue color line represent the result for B100 biodiesel fuel. And the injection pressure is constant at 50 megapascal. So obviously you can see that at the beginning, in terms of liquid penetration, before 1.0 millisecond, sorry, around before 0.8 or 0.7 millisecond, the what I call the liquid penetration is same for B100 and also D100. However, after 0.8 millisecond, we can see that um, the liquid penetration for B100 is greater than liquid penetration of diesel fuel. Okay, so we can conclude that from the result, liquid penetration for B100 is greater than liquid penetration of diesel fuel. Okay, in terms of vapor penetration, S value, so we will have the second graph where at the beginning around 0.1 until 0.0 until 0.3 millisecond. So the vapor penetration is 0. However, after that time, you can see that the vapor penetration increase for both fuel, DF and also B100. And at the end, we can conclude that still B100 will have greater value of vapor penetration in terms of distance compared to diesel fuel. For cone angle theta, we will have at the beginning static increase of cone angle. Okay, so from 0 to around 20 degree. After that, we can see the pattern of different what I call value of spray cone angle for both fuel. However, you can see clearly from the graph now diesel fuel has greater spray cone angle if you compare to biodiesel fuel B100. So as a conclusion for cone angle, spray cone angle for diesel fuel is greater than spray cone angle for biodiesel fuel B100 at injection pressure of 50 megapascal. So I call the graph that I show in this slide, actually the graph provided here actually were redrawn based on Hawi et al. 2019 result. So I just pick the important result for D100 and also B100 in order to make the comparison. Okay, few spray behavior tests in terms of possible effect in fuel deposition. So first, from the result obtained in previous slide, we can conclude that in terms of fuel spray behavior for diesel and also for biodiesel. So in terms of vapor penetration for B100 is greater than D100 diesel fuel, and liquid penetration for B100 also greater than diesel fuel. However, for cone cone angle for diesel fuel is greater than cone angle for biodiesel B100. In terms of effect, the penetration effect on deposition. So if you look in this schematic diagram, let's say we consider in actual engine, we consider the fuel injector without wall, without impingement, fuel impingement on the wall. Let's say we consider shorter penetration, uh, that include both vapor and also liquid penetration. Okay, so this schematic diagram shows the shorter penetration without wall impingement, without fuel impingement on the wall. However, if we consider fuel spray impingement on wall for the same penetration distance, so we'll have this kind of condition where the fuel spray will impinge on the wall, and the wall refer to the combustion chamber wall. Okay, so from this shorter penetration, so we will have smaller impingement area. Okay, so if the fuel spray impinge on the wall, on the hot wall in actual combustion chamber, so this condition probably will give a lower deposit formation tendency. However, if we consider longer penetration, let's say now we consider without wall, so we have this kind of fuel spray features. However, when we consider wall, so we will have fuel spray impingement on the wall. So we will have this kind of condition as shown in the schematic diagram, and we will have larger impingement area. When we have larger impingement area, when the temperature, when the wall involved is hot wall in the combustion chamber, so we will have higher deposit formation tendency. Okay, so longer penetration will cause higher deposit formation tendency compared to the shorter penetration. In terms of cone angle effect on deposition, so for the case of small cone angle, if the fuel spray impinge on the hot wall in the combustion chamber, for the smaller cone angle, so we will have smaller impingement area, and smaller impingement area will have lower deposit formation tendency. However, if we consider bigger cone angle value as shown in the figure, so we'll have larger impingement area as shown in the schematic diagram, and larger impingement area will cause higher deposit formation tendency. So from this I call possible effect of spray behavior to the fuel deposition, we can conclude that in terms of vapor penetration, deposit formation for B100 will be greater than diesel fuel. Similarly, if you consider liquid penetration, deposit formation for B100 or diesel fuel will be higher than diesel fuel. Okay, so based on cone angle result, so the cone angle result for diesel fuel is greater than cone angle for biodiesel fuel. So if we just based on this parameter, so we'll get more deposit obtained by diesel fuel compared to biodiesel. However, we can only based on this one because what I call B100 have many criteria or many factors that will cause greater amount of deposit formation compared to diesel fuel, such as the high density of B100 fuel, and also the different behavior and higher drop lifetime compared to typical diesel fuel that cause greater amount of deposit will be accumulated for B100 compared to diesel fuel. Although the cone angle for diesel fuel is greater than biodiesel fuel B100. Okay, now we will discuss about fuel spray deposition test. So this test actually the second part of fuel spray test category. So this test actually is an investigation involved with deposit formation at specific surface temperature due to fuel spray impingement. Okay, so now the photo or the figure shows the spray behavior or spray characteristic. So in this test, the tested fuels are B5 and also B10. Sorry, B10. So 5% biodiesel fuel and also 10% biodiesel fuel in fuel. And the temperature of surface was set at 300 degrees Celsius. And this is the what I call this a simple apparatus for fuel spray deposition test. So we have numbers of component here where we have electric motor to run the fuel pump. We have DC 12 volt power supply to provide power to the fuel pump. Fuel tank is used to store the B5 or B10. And fuel injector will provide fuel spray that impinge on the hot plate. Okay, so we have heater here under the hot plate to provide heat, and this heater was controlled by using temperature controller to maintain the temperature at 300 degrees Celsius. So we have two type of hose, exhaust hose to suck the what call the vaporized fuel to the surrounding, and also we have the second one is reservoir hose to remove the liquid fuel that released from the fuel spray. Okay, so in terms of tested fuel, so we have B5 and also B10. In terms of temperature, surface temperature, we set at 300 degrees Celsius. Okay, so in terms of process, first we run the what I call the fuel pump by using electric motor, and then the fuel pump will pump the B5 or B10 from the fuel tank to produce fuel spray, and this fuel spray will impinge on the hot plate, and the vaporized fuel will sucked by the exhaust fan in the exhaust hose. So in this experiment, at every 10 minutes of fuel spray impingement on the hot surface, amount of deposit accumulated was measured, and its deposit feature was captured by using a camera. So these are the basic process of the fuel spray deposition test. Okay, fuel spray deposition result. So this photo shows the result I obtained for B5, and this photo actually shows the deposit features when the fuel spray impinge on the hot wall or hot plate. So for figure A and also photo A and photo B, we can see that B5 obtained circular pattern of deposit formation, and most in terms of type of deposit actually still in liquid form. However, for photo number C until photo E for B5, we can see that the increase of the formation of black color deposit on the hot surface, and we will have droplet flow like pattern of deposit on the hot plate. Okay. However, for B10, from photo F to photo J, so photo F after 10 minutes of spray impingement, so we'll have same droplet features same as B5, where we have circular pattern of deposit on the hot plate, and the what I call deposit still in liquid form. However, for the rest, start from photo G up to photo J, so we have droplet flow pattern of deposit, where this kind of droplet flow pattern shows that more I call amount of fuel of B10 remain on the hot plate compared to B5, and this clearly can be seen in photo G up to photo J. So based on this result, it is seen that more liquid fuel remain on surface for B10 compared to B5, shown by more droplet flow pattern on the surface. At surface temperature of 300 degrees Celsius, B5, if we base on the evaporation characteristic, B5 vaporization rate is higher than B10. So B10 will has greater tendency of deposit formation compared to B5. So these are the conclusion and also the result that obtained from the call the observation of the basic or general features of deposit features that captured by using a camera. Okay, so the result in terms of mass of deposit accumulation on the hot wall. So every after every 10 minutes after the spray impingement on the hot wall, so the amount of deposit accumulated on the hot surface will measured. Okay, so now after when we obtain the what I call the mass of deposit accumulated, so we plot this graph where we have a deposition mass m in gram versus time for every 10 minutes. So the graph with what I call with blue color line represent the result of deposition for biodiesel B10, and the dash green color line represent the result of deposition for B5. So clearly we can see that at the beginning the formation of deposit for B5 and also B10 almost similar for the time below than 10 minutes. However, after 10 minutes, we will have a different pattern of fuel deposit development for B5 and also B10. So B10 obtained at the end, B10 obtained higher amount of deposit compared to B5. So both B5 and B10 have similar deposit development at the initial stage of deposit formation. As the time increases, B10 accumulate more deposit compared to B5. So the difference of deposit accumulation between B5 and B10 keep increasing with time. Probably formation of deposit layer altered the heat transfer process during the deposit formation, as shown in the schematic diagram. Okay, so we have first layer, for example, if without deposit formation, for example, if without deposit formation, the surface temperature is 300. When the first layer of deposit formation form, the surface of the deposit may be reduced to 295 degrees Celsius. And when the second deposit layer form and more deposit accumulated, so the surface temperature keep decrease, and this will affect the deposit formation for the later impingement of fuel spray. So the decrease of deposit surface temperature depend on the deposit thickness and its thermal conductivity. So this is one of the factors that we need to consider in explain the deposit development for different type of fuel on the hot wall.